We are Group 14 and this is the presentation for Design of an Agitation Mobile in CFD. Mixing is a unitary operation which aims to homogenize a mixture with more than one component. It consists of three main parts: the motor, an agitator or impeller, and the tank. Baffles can be added to the tank to prevent serial generation, which lowers the agitation efficiency by making the fluid flow pattern homogeneous. There are two types of flow in the mixing operation: axial flow and radial flow. Axial flow is generally used for suspended solid as it tends to have an effective top-to-bottom flow pattern and generates a homogeneous mix throughout the tank. Radial flow tends to form two different mixing zones in the tank, on the top of the impeller and below the impeller. The objectives are to generate a new impeller design and simulate both the new model and the Russian model, to find the potency, torque, shear rate, shear stress, and power index of mixers with a Russian impeller and the new design, to determine velocity profiles of this process and compare the behavior in laminar, transition, and turbulent regime, to compare between impellers and recognize the behavior for each one. Methodology. Design of the new impeller. This design represents an axial flow impeller. This new impeller has 4 open blades inclined at 45 degrees to respect the agitator. The mobile device has the restriction set so that the shaft has a diameter of 8 mm if not exceeds 51 mm in diameter and has a maximum height of 10 mm. The tank for both impellers has a 140 mm height and 140 mm diameter. It has 4 opposite baffles, 25 meters long and 4 mm wide. It goes from top to the bottom of the tank. While trying to obtain information from all the kind of flows, turbulent, transition, and laminar, we made simulation with 6 Reynolds, 2 for each kind of flow. The rotation speed of the impeller, the maximum simulation time, and the necessary time intervals are calculated from the Reynolds. The geometry contains 2 main parts: the rotating zone and the total volume. The polyhedral mesh was made on the system. Custom controls were carried out in the interface between the 2 volumes, so that the amount of cells between these 2 volumes are higher. The prism layers of the new ones were eliminated in this interface. We used every report given in the guide for the project and carried out every report needed for the analysis. K omega was used as a model instead of K epsilon because it tends to be more exact near the walls of the surfaces. We used water and mineral oil with the given viscosities and properties for the simulations. Results and discussion. First, we obtained the power number against Reynolds for the new impeller and for the Russian impeller, which was given by the parameters of the project. We then can look at the graphic, which are similar and have a similar behavior, where the main difference is the first value of the power number, which is way higher for the new impeller. When comparing the values of torque, shear, power index, power and shear stress for the new impeller and the Russian impeller, we can see in the graphs that the new impeller is has higher values for all of them, which means it has better mixing and better energy transfer to the fluid. When the power number obtained in simulation was compared to the one obtained in the paper, which compared the same type of impeller, changing the blades angles from 45 to 60 and 75, we can see that it behaves similarly, and that by augmenting this angle there's a greater energy transfer to the fluid, so this could be a way to optimize the new impeller. When comparing directly the shear stress from both impellers, we can see that the new design has a larger shear rate, which means it's better for viscous mixing because it breaks the molecules of the fluid, making it easier to mix in an homogeneous way. While trying to compare each of the impellers, we can clearly see that there are two different type of flows in here. There's radial flow to the right, which clearly generates two sounds, two patterns of mixing, one on top of the impeller and one bottom of the impeller. There's an axial flow, which generates one flow that kind of goes downwards, then crashes to the wall, and goes upwards, kind of a circular motion that connects the whole volume. The new design velocity pattern, on the other hand, has a higher velocity and clearly has the actual flow we talked earlier on in the presentation. In the Russian velocity profile, we can clearly see the fluid flow radial flow impeller generates with its proper velocity given of the impeller. To make sure the mesh was correctly done, we did a J plus wall tool, in which you can see here that the impeller tends to have a small number of wall J plus, which means there's a high number of cells. Still, there's some important places like the plate, some zones in the plates where there's a very big wall J plus number. This means that there is not as big amount of cells as you would like. So a probable way to make this simulation better could be to increment the amount of cells in these zones that are of great importance, and so to increment the amount of data that goes through these zones, and so have a greater certainty of the information obtained. To conclude, it can be said that we obtained reasonable values for the Y plus wall tool, even though some parts of the impeller had a low amount of cells. So if this was increased, we could optimize the results for our impeller. Also, we appropriately did the design of the impeller, we recorded data necessary and compared the new impeller with the Russian, where we found that the new impeller is better than the Russian for both viscous and non-viscous fluids. It can also be concluded that the new impeller was correctly compared to one found in the paper, where the power number behaved in a similar manner in both cases. And so the design for the impeller is a good proposition for an impeller.